Welcome to Simulation and Prototyping. In this tutorial, I want to introduce a couple of important concepts. First is logic, or in other software, these can even be called rules or rule firing. And what we're going to do is to define a couple of conditions that will separate our definitions so that it will create a kind of A, B, or C condition. And then that way we can allow different set of actions to occur from that point forward. And so this notion of logic will use different types of approaches, greater than, less than, other types of things for this to occur. The other thing that I want to start doing is being a little more explicit about where we kind of hold our parameters. And so an idea that we might have a global parameter that might apply in multiple conditions. We change that in one place and it affects a number of things. And then there's local parameters that are driven by localized conditions. And so we'll see the way that these two things work. There's a couple of interesting advancements as it relates to playing with some simple math and allows us to separate out some really kind of simple things that are happening. And then we're also going to be color coding in the follow-up tutorials that come after this one. So what you see on the screen now are a couple of girders and columns. And eventually what we're going to do is to also create rafters between these girders. You can see a couple of other things. We see dimensions at each column. These are the heights of the columns so that we can manage that. And as we make decisions, we can start to see what will occur with that. And the other thing, if you look carefully, you'll see two girders, and we see a different set of conditions, kind of different amount of cantilever at either end. We see a different amount of columns. And what we're going to do in this first tutorial is to develop an approach where all we're doing is creating one line, and this line will allow us to figure out the columns. But I want you to see what happens that there's going to be three conditions that we're going to work with. I have a maximum cantilever dimension set. So all of a sudden, when that rule is no longer taking precedent and that we exceed that, we see a different thing happens. All of a sudden, this was then subdivided a different amount and that cantilever goes away. As I reduce this, we can see a cantilevered condition. We get smaller and smaller to a point where the kind of maximum spacing between columns is achieved. They get closer and closer until all of a sudden we drop to another condition where we can use a cantilever. And then as we get, here's a third condition, or a third rule, is that when the beam gets so small, there's two columns with cantilevers. The cantilever will slowly reduce. And then as it does, a third rule will take effect, which we may or may not use at all in this case, but that we have two columns and the girder spans simply between those two columns. So what I want to do in this first portion of the tutorial is to work through how this is working. It's a little wonky. We can make it a little lower. But work through these types of issues and help you understand how we use these logics and how we kind of filter these out to allow the different resulting procedures to occur. And so you can see we just went from two columns, two columns, two columns, to a point where a different rule will take effect when we start cantilevering. And once we pass beyond the maximum limit of the cantilever, a new set of rules take effect. And basically what I'm doing is I've set some arbitrary numbers. I'm saying that this is the maximum space between columns is 12 feet. And the maximum cantilevered amount is 4 feet on either end. And so let's look at how we do this. For this tutorial, I'm going to, I should save this first just so that I have it. We're going to work in inches this week because we're actually going to be dealing with the depth of some of dimensional lumber. And so I want to be able to use that as our default unit. So we'll start with large, new object that's large objects in inches. And I'll start a new grasshopper as well. So I think we can just use one curve here. I'm going to set my orientation down at the bottom with X and Y as positive. So I'm going to start here and move to the right. And why don't I start with something that is, let's say 120 inches. And so that's a good starting point. Now I also have a frame of reference for, that's 10 feet, and the maximum beam or girder span length will set to 12 feet. And again, that'll be a global parameter that we can change. So let's start by capturing the curve, and we'll use a curve container. We'll set the curve, and now we have that. First thing that we're going to want to do is determine its length. And so we can get the length component. We'll plug this in. We're going to use a lot of panels today just so that we can track the inputs and outputs for a number of things that are going to happen as a kind of diagnostic, so that we just have a sense about exactly what's happening. So now we know that line is 120 inches long. That's nice. Let's set up this kind of condition, and I have a little bit more foresight in terms of where we're going to end up. And as has been my convention, any parameters that I want to have as kind of inputs, I pull to the left. I want to be even a little more extreme today and maybe make, I wonder if I can even just make, I can't make a box. Maybe I can, but I'll leave that alone for a second. But I want to make a couple, starting with a column on the far left that'll be global parameters. And so I'll do this with a panel. And here I want to name these. And so I'm going to right click and change the name of panel. And let's call this one max beam span. And we'll set this to be 144. Can make it a little smaller. And basically what I'm going to do is say, okay, this column in the far left will be my global parameters. Moving a little bit more to the right might be inputs that I need along the way for geometry. And then we'll start our definitions to the right. So this will start to make a little bit more sense as we go. So with this, let's now figure out, we know we've got a kind of line that we're working with here. We know its dimension. Let's now let's figure out how many divisions it has if the maximum span is 144 inches. And so this is a kind of simple math, but a kind of useful thing for other types of divisions that we might use in the future. So let's use division, and let's divide our length by our maximum beam span. I'm going to create another panel so we can see exactly what comes out of that. And we can see it's less than 1. And that's okay for what we're doing. As I pull things from the global parameters, I want to use these as the hidden wire displays, just so that we don't have all of these lines. We know if we click on this, we can see where it connects to. And so we'll try and be a little rigorous today as that happens. I'm not always super rigorous in terms of working through that. So let's get to a point where, so this is our first condition, that we have a beam that's less than our maximum allowable span. And so this will be one of our conditions. And so I'm going to move over a little bit and start to create a set of rules that our geometry will work through and come through to the other side. I'm also going to use I'm going to use a panel as a way to name these. And my first rule, and let's just call them rules, will be if less than max beam span. And I don't actually need a title for that because I'm just using this as a label. And what I may also do is change its color. And I'll keep these kind of color coded. So this is like, okay, maybe blue will be our rules. Now let's look at the way that a simple rule works. And for these, I'm going to use under math or maths, it is plural, I don't know why, but under math, under operators, we have a few things here. We have equal to, larger than, smaller than, and then similarity. So let's use a condition about smaller than. And what we want to do is we want to test, is something true? This is a Boolean operation, true or false. Is a certain condition achieved or not achieved? And so our first number will be the length of our beam. The second number will be our maximum span. And I will make that a hidden display. And let's see what comes out of this. So I'll use a panel here as well. As I already said, lots of panels today. True. And maybe we'll just diverge for a second, and let's build a really simple example of this so that we can test it in a very, very basic setting. So let me make 2 sliders that come in. And so with this, right now we're just isolating this for a second to look at it. And why don't I set both of these sliders to 5. And so the question is the first number, smaller than the second number? And so what we see coming out of that is smaller than or equal to. And so here we have, is the first number, is 5, smaller than the second number? Simply, that's not true. Is the first number smaller than or equal to the second number? That is true. Let's see as we change these, as we move this down. Is the first number smaller than the second number? Both of those are false. As we move this past 5, is the first number smaller than the second number? Both of those are true. And so we can use these logics, true or false, and this will either give us 1 or 0 as a way of coming out of this to control a set of other functions. And so let's build this kind of simple thing right here. And under, let's see, sets and under tree, there's a couple of other useful tools to use these in combination. We're going to make use of a stream filter today, but just as a way to introduce this, I'll also include a stream gate. So stream filter and stream gate, imagine that there's a stream of data coming in. Stream filter allows us to bring in multiple types of streams and then choose which one proceeds through it. So it's a kind of like a dam, right? We let some things through, or filter, I guess exactly like it says, we let some data through while we hold other data back. The opposite is true of the stream gate, in that we have data coming in, we can let multiple data out. And so we can see the key difference. Both of them have a gate. Stream filter has multiple streams coming in, and we can add more. So we can have many, many things coming in, just as long as we understand how to filter that, and only one coming out. Stream gate, on the other hand, can have only the gate and the stream coming in, but then we can have multiple outputs. And so filter, many things in, one thing out. Gate, one thing coming in, and then splitting that so multiple things can come out of there. So what we're going to do now is we're going to use the stream filter with only 2 inputs, and actually only really 1 input in the way that we're going to build this today. So let's say we're going to use this. I'll show you how it works. And let's say that the gate, actually, I just did that wrong. So watch what happens when we do this. And we'll just use a panel on the other side. So if the first number is less than the second number, if this condition is true, what we're doing is we're passing that first number through. We could also set this up so that if it's not true, we can pass the other number through. So let's change this number to 5. So that'll still be 5. If this moves to here, now we see we're getting the smallest number out. So we're comparing 5 or 3. And then depending on whether the gate is true or false, and remember, false is 0, true is 1, and we're using that Boolean condition, 0 or 1 here, to decide, or do we let 0 or 1 through? And so you can see S1 is when it's false. If I increase this other number, you see S turned into 1. And so this gives us a little readout about which stream it's allowing to come through. And we can see on the panel on the other side that it's always going to allow the smaller number through. So it's either going to be 5, or it flips to the other slider when this one is smaller. And so these are the kind of rules that we'll use now. We'll use this simple set of components to build now a logic into, when we draw our line, how many columns get added to that beam. So let's leave, well, we can get rid of this. We've got the start of it up here. So what we're doing is we are comparing these two, and actually I'm going to have it smaller than or equal to. So as long as my beam is 144 inches or less, I want this to be true. So those columns can sit anywhere up to 12 feet, 144 inches. As soon as it goes beyond that, I want to trigger a different rule. So let's look at how we do this. So here's our beam. It's just a simple line right now, and it's going to get smarter and smarter in a few minutes. But let's, with this set, with this kind of rule, let's get the endpoints, because that's what we really want. And so let's pull in our curve. We'll capture our endpoints with that. No matter how long this is, as long as it's 144 inches or less, we want to have those 2 endpoints. And so that will be, I'll use a point container. And I can add the start and the end to this for that 1 point container. And then here I'll use the stream filter. And so the gate that's coming in will be the Boolean true or false. And then the stream, in these instances, what we're going to do is we're going to build the rules independently. If the condition is false, we don't want it to pass any data through. If it's true, we do want it to pass through. So what I want is I want to get the points only if these are true. And so when this is true, then we get a series of points that come out. And so I'm going to also make a point container on the other side, just so that I know what that is and what I have to work with. And so we just built our first rule. Let's group these together. And so we have a nice little block that's here. Let's see. Now let's build a couple of things that happen around this. So first of all, we want our beam to have some thickness. And so if I move my points in space, and move them up a little bit. Not sure I just moved it up. And we have this beam. Let's extrude it. And so we can set this up, even running maybe parallel to our rules. And so up above this, why don't we make a simple extrusion? And so I want to extrude the geometry, and that will be my curve. Is our base to extrude. And the direction will be the Z direction. We just want to extrude it straight. And I want to use another global, what I'm calling global parameters. And so I'll use a panel because this is something that we'll just type in. And I'm going to set this, if I right click and change the name of panel, I'm going to set this to be the girder depth. And I'll set this to be, I don't know, we can change it later, maybe 24. So the girder is going to be 2 feet deep. And let's plug that in to our Z value. And let's see, I want to, because it's a global parameter, let me do our hidden wire. And so these just sit over on the side. This seems a little deep for how far it's spanning. And we can always change it later. We could also embed a rule that if it's a shorter distance, the girder can be shallower, but let's keep this simple for now. So I'll set these two in a kind of column related to our rules. The other thing that I want to do is I also want to, we'll need this for later, our line, I want to move a line up to the top of the girder because we're going to use that to set our rafters later. So let's just move our extrusion, or not our extrusion, we'll move our line. So we'll add a move. And the geometry is going to be our curve. So we'll pull our curve over to the move. And our motion will be that same Z vector. And so if we hide the extrusion for a minute, we see we have the line that we've drawn, and we see we have a line that's been moved up to the top of the extrusion. And so we'll have both of these for later. Let me do one more thing over here using this as a kind of stream of what's happening kind of no matter what, is I want to create columns. And so let's project down our, let's see, maybe that'll come later. So we'll do it on the right side, and this will be a condition of what comes out of our streams. But since we have our first one and we have these 2 points, let's build a column. So the way that we'll do this is we're going to project the points down to the C-plane. And so let's use project. And so we can see project an object onto a plane. What we want to project are our points. It defaults to the XY plane, but let's just own that and give it the XY component. We can hide that. And now we see that as our line moves up or down, left or right, those points that exist up above the XY plane are being projected straight down as they hit the XY plane. So that allows us, as we change our curve that's controlling our beam, we get the relationship between these. So with that, we can make a line just using the 2 endpoints. So the start will be our points that are coming out, and the end will be the projected lines. So now we get the centers of our columns. And let's pipe this. We could just as easily leave them lines as well, but we can pipe that. We don't necessarily have to cap it, and we do have to add a radius. I'm going to come all the way back to the beginning, and I'm going to create another, I'm calling global parameter, and this will be the column radius. Let's say these columns are 4 inches. The radius is 4 inches, so we'll create a panel. I'm going to right-click it and change the name of panel to be column radius. We'll double-click it and set this to 2. And so we can pull this parameter all the way over to our radius. We see that our columns just got a little bit beefier. And let's set this to be a hidden wire. And so now that works. So let's hide our projected lines. We can hide our points, and we can hide our lines. And we also have to hide the stream filter. And what else? And our endpoints and our point. So now what we end up with is just our girder and our columns. If we move our line up or down, the columns are following, and that's looking good. All right. Let's make a new rule. Actually, let's see what happens with this. So as we move our points in space, we can see it's a little bit off the orthogonal. So we can get these to be a little more orthogonal. If I move the point back as it gets closer and closer, it's simply dividing. Well, it's not even dividing. It's just giving us the endpoints of our curve. And that's what we need. That works well as long as we're less than 144 inches. As our girder increases in length, we'll see that it continues to be one single span until it doesn't. And so let's see how far we are now. We can track this. We're at 133 inches. We'll go a little bit more. We're at 142 inches. The next amount I pull, we see our columns go away. And that happened because our stream filter now became false. That our girder was longer than, not shorter than, it was longer than our allowable distance. And so that switched. If I move back slightly, we'll see this change to true, and then it will feed us that point. Now it became true. Now we get the points in our columns as a result. When we exceed this, now they go away. So this now gives us the next condition, because all of that works while this first rule is firing. All of a sudden, when we're out of the range of what we've set for this first rule, we don't get any data coming out, which means that we'll build now a second rule for this, which will take over when this rule doesn't fire. So let's build this now. So we'll do a similar thing. Let's create a description for us. And this will be if, well, the other one was if less than the maximum beam span. This will be if greater than one beam length and less than the maximum cantilever. And we'll see how this plays out in a second. So if the first rule is it's less than, it's less than, it's less than, now the next one is all of a sudden it's greater than, let's build a component that rather than saying smaller than, so under math and under operations, we'll do larger than. And so is the first thing, is our curve larger than the maximum beam span? And we'll have another panel. And in this case, we don't want to duplicate because the previous one goes from up to 144, and we said equal to 144. Now, as long as the line is greater than 144, if we set them both to be greater than or equal to or less than and equal to, we would have a problem because at 144 exactly, we would get two trues. We want to make sure that we have a kind of binary condition between these. So if the first one is set to smaller than or equal to, the next one we should use larger than. And so now we can see this one is already true because the previous one is false. And so now let's look at what else happens. Our rule that I wrote was also a little bit more complex. If less than maximum beam span is the first one, this one had two conditions. If it's greater than one beam length or maximum beam span, and it's less than the maximum cantilever. So let's add a less than. So we'll go to operators, smaller than, and we'll plug this in. And so now we have to figure out a couple things. We have to do a little bit of math before we get here to understand this. But I can add the panel data to come out of that. So let's look at our maximum cantilever. First of all, let's set a panel as a global parameter so that we can control this for all of the beams that we'll make within this. We'll right click, and this will be maximum cantilever. And I'm going to set this to be 4 feet or 48 inches, but there's 2 cantilevers because we're going to split the difference of the overall length. So I'm going to multiply this times 2. In the end, we'll divide it by 2 to get a specific dimension that we're looking for. But for now, we'll set this to be 96. So we can plug in our maximum cantilever as our limit, or as the number we're comparing to for the second number, because we want the first one to be less than. So now I'll make that hidden before I do this. Now let's figure out how to do this. We're going to do a couple of things with the division. If we look at the overall length, of our curve, we can see that it's 163 and a little bit, and the maximum length was 144 for a beam span. This means that we have two things happening. It's 1 and a little bit more. So what I want to do is I want to split apart the understanding of the length into two parts. And what that's going to be is, first of all, and there's a couple of different ways we can do it. I'm going to use an expression, and we only need one value coming in. I'll set it to just be capital X, which is easy. I want to pull in the result of the division. And what I want to get is what's called a fix. I'm sure it's called something else in other places, but here a fix is simplest formula, fix X. This returns the integer portion of a number. And so let's set this to be fix, parentheses, capital X. And what will come out of this should be 1, which seems super lame right now because it's only 1, we're just dividing it by 1, but we're also building into the fact that as we make our line longer, there can be multiple divisions. So right now what we're saying is that we've got 1 maximum beam span and we have a little bit left over. And so the bit that's left over, let's check that. We could always subtract the number of divisions from whatever's left over, but there's also another operator called modulus, and this will return the remainder. So if we take our first length, the length of our beam, and divide it by our maximum beam span, which it didn't like, let's divide it by our fix. Divide two numbers and returns only the remainder. Let's see. What doesn't it like? Invalid cast, primitive data type. We don't want our curve. We actually want the length. That would be a number. So now we can divide our number. Let's do that by 144. And let's see what we get out. We should get out so what we're getting out from the modulus is 163.707 minus 144. And so that's the remainder that exists there. And so remember that what's left over, we're going to use as the cantilever. And so that will be the modulus will be our first number. So is the remainder that's left over when we take out maximum beam spans, the cantilever, is the cantilever less than our allowable cantilever length? And so our global parameter that we set for the maximum cantilever was 96 inches. Now the remainder is 19.7. And so that's true. So within our rule, we're going to add one more thing before we get to the stream gate now. And that is that we said if it's larger than the beam length and less than something else, the and, as we write these rules or these logics, is an important thing. And so under our operators, we see that we have what's called a couple of gates as well. We have an and, an or a not gate. And so when both of these are true, the gate will be fed to our stream filter. I'll just disconnect both of these things so it doesn't confuse us in a minute. That can happen. And so this stream gate, or this gate, this AND gate, will allow us to plug in A and B. This will only be true when both of these are true. So when I plug in the result from this, when both of these are true, when A is true and B is true, this will be true. So this will be our gate. And from this, let's see what we'll plug in. We're gonna do some more processing, whereas before we just pulled in our endpoints. Here we've got our logic, and we know this is true, and so we'll have whatever comes into stream 1 when both of these are true. So I might even just flip these, knowing that we're going to do, now we want to figure out what we pull out from our data to construct our columns. So let's start with this. Let's grab our endpoints, and rather than pull these from above, from these endpoints, I just want to have my rules as kind of freestanding elements within our definition. So let me pull in the curve. And here I want only the start point. So I'll make a point container for the start. I'll hide my endpoints. And now I have my start point. And what I'm going to do is I'm going to now create, I'm going to move these along the length. And I'll tell you, I spent a little bit of time. I was like, oh, this could be a loop. And it could be. The way that you might program it in other instances is that we would start to duplicate points along the length. We can do this using a range and moving these things along the range. So let's start with multiplying. So now we have our start point, and let's work out a couple of things. And it's going to be a little strange when we start, only because we're using one length, but we'll make our line longer, and we'll see what happens with that. So I'm going to do a multiplication. What I want to do is multiply our fixed value, that one integer that's coming out, by our maximum beam span. And this is going to give us a value that comes out of that. Which will be the number without the remainder. And so I want to, again, hide my lines. There was one other line feeding to somewhere, feeding to our modulus. Make that hidden. So again, our global parameters are sitting over here on the left, because we're going to take all of this big block of sets of Grasshopper components, and we're going to start copying them for each beam that we're going to make. So now we know that we're within a range, and our two columns, given this condition, will be 144 inches. And so let's use that, and we're going to make a range. And with a range, we'll need a domain. So we'll construct a domain. And we're going to start at 0. That's okay. And I'm going to use the multiplication of how many beam spans we have times their dimension. And so now we'll have a domain from 0 to 144. We'll set that for the domain of our range. And the number of steps will be our fixed value. And so let's see what comes out of our range. We'll have another panel. And we have 0 and 144 as our range. As this increases, maybe we should increase this just to see how it works. We'll have to increase it beyond. There we go. We just came beyond one length. So now we have 2. We go from 0 to 144 to 288. We just get those simple multipliers of what's happening. So now let's move these points, or this range. Right now it's just a range. I want to turn them into points, and I want to use our start point as a way to do that. So let's move. And what I want to do is it's not enough if we just plug in, let's say, our start point. We can't plug in our range into the motion because we have to set the motion. We already know in the way that we've been fussing with the curve that it's not going to be in an orthogonal relationship. So what we can do as a way to get its vector is, and I don't know if we've used this vector before, I assume we have, but we know that we have X, Y, and Z vectors, but we're going to get a unit vector. And a unit vector allows us to, allows us to capture the direction of a particular line. And in our case, this line is going to be set from our curve. And so let's pull our curve into our unit vector. But this, as a unit vector, it doesn't give us any dimension. And so let's multiply our range with our unit vector. This then will become our motion. So look what we got now. We've got a point at 0, 144, and 288. And so that looks good for us. The other thing that happens though, because, and we're just beyond the limit of 2 beam spans, let me pull it a little bit more, and we'll see what starts to happen is that we're still within, let's see. So we're at 355. So if we took 144, multiplied it by 2, and added 96, we're still within that range. We're cantilevering just at one end. Because of the way that I want to work, I want to split the cantilever on either side. And so let's just test our rule first, although I guess nothing's going to happen right now because we're not really using the rule yet. We can see as we increase beyond, we're just adding a column when we exceed 96 for the cantilever. Or we're not quite using that yet. So what I want to do is I want to shift our columns to center them so that we get the cantilever on either side. So let's take our modulus, and I want to multiply our modulus by 0.5. Right? I want to take half of the modulus, and I want to shift our points by half the distance. So let's find our modulus, which is up here. We'll plug this into this new multiplication. Our output from this will then be half of the remainder. So if we go check on that, knowing that this is 37, our modulus, the remainder, is 75. So that makes sense. And now let's just move the points that we have. So I'll copy that move function. We'll use the new points. We'll move these, and we'll move them based on half of, well, and that didn't work because what I have to also do now is I'm going to add another multiply. I want to multiply this times the unit vector. Plug that into the motion. So I'm going to hide my first move. Now what we end up with, and we can also hide our first point now. What we end up with is a series of divisions for our columns with a cantilever on either end. So let's test this a little bit and see what happens. And our last rule is going to be what helps us get to a point when the cantilever is greater than a certain dimension. Although let's see, it seems that maybe we're not even getting that condition anymore. We're always cantilevering, but if the cantilever, I thought we had a condition where the cantilever exceeded, my guess would be, okay, so right now our cantilever is exceeding because half of the cantilever is, let's see, our total cantilever here when we look at the modulus is 128. It shouldn't be greater than 96. And this is a value that we want to set over here. So we do need a third condition. But before we do that, let's finish out this stream. And so let's see, where was our stream filter? It was over here. So we're going to plug it into number 1. And then this is technically not giving us anything right now. And let's pull this over. And what do we need to plug in? We need to plug in both the geometry that's coming out of our stream filter. We're going to hold down Shift. And we're going to plug in the start points for there. So we plug them into the project. We will plug them into the start points, holding down Shift. Nothing's happening because nothing is coming out of this stream yet either, because let's group these together. Because we're exceeding our rule. So let's make this a little bit shorter. And what should begin to happen, now we get our columns as our rules are met. And that's working. Because it's true. Watch what happens if we make this a little bit longer. We will exceed the cantilever dimension, and once we do, this one will turn false. And so once it turns false, we lose our columns there. And so I also want to hide our points. And so then that's clean again, which sets us up for our third condition. So let's build our third condition. I know this is going to be a long tutorial, but I want you to be able to understand the way to deploy some of these decision options as we build things. Your definitions will get so much smarter as a result of these. So the next one's going to be pretty simple, given that we just developed that one. The difference will be, if the previous one was if greater than beam length and less than max cantilever, this one will be if greater than beam length and greater than the maximum cantilever. And so let's look at how that plays out. So far we've had smaller than, now we've had larger and smaller than. The next one's going to be larger than and larger than. So we'll have bring in two larger thans. And actually, the first one, why don't we just copy, because it's going to be the same inputs. And we can even bring our AND gate with it. And then our AND gate, instead of the B from above, will pull the larger than the cantilever. And so Let's add a panel to see what comes out. There's no data coming out because we haven't plugged anything in yet. Let's grab, so we're going to pull our modulus. We're going to test that against our maximum cantilever. And let's see. And right now that second one is false because we know that we're under that length. Let's move this to a point where it becomes true. We just saw this now flip to true. And now we're making use of our third rule, although nothing's happening yet. So what do we want to happen with our third rule? Let's see, first I want to hide a hidden wire from there. Okay, so now our rule is set. We have this telling us or firing if these things are happening. We know we'll have a stream gate or a stream filter that comes out of this. Our gate will come from that, and we'll plug into stream 1 in a second once we figure out what it is that we're going to do. So in this case, what we want to get are both of our endpoints. So let's grab those. We'll pull that from our curve. And let's get point containers for each so that we can control these. We can choose whether we're using our start or our endpoints. We see those show up in the geometry on the right. And let's now do a similar thing with our range. But what I want to do is, because we exceed the maximum dimension of our cantilever, what we're going to do is we're going to choose to add an extra division into that. And so what does this mean? So let's make our, let's see, we'll have a range, construct a domain, plug that in, and our domain is going to be just like it was before. It's going to be from the start to the next, let's see, what is our domain? Our domain now is our overall length. I'm going to plug in our overall length and see what happens so that we work with that. So the end of our domain don't remember off the top of my head, so we'll work through this and we'll see what happens. The end of our domain will be our total beam length. The number of steps, though, if I plug in just simply the fixed value, can add a panel and see what we get out of our range. That's what we get within our range. But actually these, we can see, already exceed our maximum beam length, 168, as opposed to 144. So what we can do as a way to, with our range, is we can add 1 to our fixed value, to our kind of, to the integer that comes out from that division. So now, if we add 1, here I know that what I did a second ago, I'll just add that, make this a little easier. And now let's change this out for our steps. Now we can see our number of steps are all less than 144, it's 134. So that worked well, exactly like we wanted it to. Let's copy our unit vector from above because we already know that we have our curve coming into it. And let's get our multiplication as well. Pull this down. So we have our curve coming into our unit vector. Let's multiply it by our new range. And now let's move these points. And we're going to move our start point by our range along our unit vector. So now when both of these rules are true, we're going to end up with a number of divisions that make sure that these are all less than our maximum beam length. So I'm going to plug this in to stream 1. The other thing I'm going to do is plug in, let's see what we have. I think that's actually all we need because we're getting all of our beam lengths there. At one point, I think I was pulling the start and end points, but let me hide these and make sure. I think in a previous definition, I was duplicating those, which seems unnecessary. So this is a little bit more elegant. We have our stream filter here with a series of points that are coming out. I think before I added a point container, but we can leave that step off. And let's we'll do exactly what we did a second ago. Let's group these together. And we can pull down these that are coming out. And let's plug in our stream filter into, holding down Shift, our projected geometry and the start points. And now we can see we get those columns. I'm going to hide the stream filter. And so now let's manipulate our, let's see, I'm going to hide the move because I don't want those points. Let's manipulate our, let's see if we can see these, if there's enough resolution on my screen. And let's just watch the false, true, false, or true, true as we move the length of our beam. And we can also start to get a sense for which is firing because the stream filter allows data to come through. So right now the middle rule is firing. We see black wires coming out. As we pull this back down, second rule, because this is true, true, and we're getting a true value out of that. Now, all of a sudden, the second rule is no longer true. We're getting a true, true out of the third rule. And so it's dividing a certain amount. And these will both continue to oscillate between those two until we get to a point where we only have one division with no cantilever, which is going to be all the way back here. Now we see our first rule firing. If we always drew our line longer than 144, we wouldn't necessarily need our first rule, but I think it was useful to have 3 rules just as a way to begin to understand a way to filter this out. So the last thing I want to do for this first part of the tutorial is to just add the dimensions, the vertical dimensions of our columns. And so let's see what we have here. So we have our pipe. I forgot to hide our endpoints, so I don't want to see those points. Let's add a 3D note, or I want to add the dimension here. And so we'll do that. Let's see, not with, we have the extrude of that, we have that. So our column exists over in the right, and we can use our projected points to locate the data for this. And so we'll use this from display and dimensions. We're going to add a text tag 3D, and the location will be our projected points. The text is going to be our what? Our dimensions. Actually, we want to add the length. So let's capture the length of our lines, of our columns. And so let's check this and create a panel. And let's check those heights. So those heights look like this. And the last thing that I want to do is, if you ever include dimensions that are too precise to a contractor, your bid will increase significantly. So let's dial back. Let's just get in the habit of dialing back the level of precision that we might deliver for something. And so we'll use an expression to do this. And it's just it's a simple, well, we can write it within, let's see, we'll use 2. So let's set variable X and variable Y. Variable X will be our lengths, and then we can set, I guess, a panel here. And let's set this to 2 decimal places, but this is something that we can change, and you can see what happens as we change it. We'll plug that in for Y. We double click, and let's see what formula we use. I think it's called round, and I think there's a typo in here as well. And it's a little bit simpler. I had to look this up last night. So it's round X, and then I think just comma Y, but we'll do round parentheses X comma Y. Let's make sure that it works. I looked it up. It took me a little while to figure out why it wasn't working, but let's say X comma Y. So then there's no syntax errors. Let's see if that works. Didn't like. So here's something that I was also came across the other day. That's a useful thing to know. So this is telling us null, 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 null. The reason being is that as we look in here, we can see that X, the X value we're supplying is a number. The Y value we're supplying is a string. Even though we typed in number 2 into that panel, this is delivering it as a string. And so what we have to do is to create a number container as a way to translate that number that we typed in. Because we put it in a panel, it sees it as a string. This will convert it, and now this expression works. And so if we want 1 decimal place, we can change this to 1. And now we see it rounding to 1 decimal place. So that seems to work well. Let's plug this result into the text. Let's set the size of our text. Can make it a little smaller. We can change the color. So let's set the swatch to just be simple black text for here. That's okay. And then we can also set the justification by right-clicking. Let's do, I think it was top right. Yeah. So top right gives us a view of the height of the column. And these are short columns. So let's change our line and double check and make sure all of this is working. We'll increase the Z value. So now this is a 10-foot column. So now we have a column or a set of columns. We know their heights, and we have their spacing along a girder. What we'll do is we have this as a component off to the side. We can group this together. And then actually, I want to pull the girder information down to the middle, because as we replicate these things, here we can pull our global data down. So our setup allows us to have all of this information. Well, even including this information is our first girder. As we replicate the girders, what we'll have to do is we can use this information for our rafters between. We have our global parameters here. Let's see what happens when we copy this. Drag it down. And let's add a second girder. Just need those 2 points. Let's set our new curve with this. We see a little bit happening. Our column heights are 0. So let's elevate our girder. We see this working. Now we have 2 independent girders. And our next step will be to build rafters using dimensional lumber, which will deploy some rules for us between these. And so while locating columns and beams doesn't seem that glamorous, I think this is a really great example of using our rules to create different conditions. And we'll see they're now firing independently. So this girder now has no cantilevers. This one does, because of the way that they're responding independently to their length. We also have now the global parameters start to make more sense, that we could change any of these. So our columns are maybe a little too fat. We just thin those up. Maybe our girder depth is a little too deep. And so now our global parameters are working on all of our beams through there. Maybe our maximum beam spacing should be 10 feet instead. Now we have additional divisions. Or maybe the weight on our roof is a lot less, so maybe that can be greater. So these global parameters then allow us to control all of the new girders and relationships and columns as they get replicated. So maybe I'll just make a little bit more space between them. And in this case, to get us ready for the next tutorial, I'm actually going to move, because what we want to do is to find and create rafters between these 2 girders. So now we're going to start to build in this space using the information that we have with these 2, which is why they're kind of mirrored now and moving about that length. And then we can also probably even copy this information and then have it mirrored with the next girder that we make. So this is a good stopping point. You should go back and make sure that you understand the way that the rules are working and how these are playing out. But we've got a really great setup now with being able to control just a couple of points and to be able to set up a set of relationships between all these things. So what we're going to build is a complex roof surface that spans between multiple girders as they move through a space. So let me know if you have any questions about this, and we'll pick up the next part. Well, I'll start right now. You can start whenever you have a chance. So hope you enjoy this, and I'm looking forward to seeing what you build.